Hello everyone, this is D. Chinnagokari. Welcome to our chemistry channel, that is Chemistry Masters Academy. So in this video lecture, I am going to explain about one of the most important concept of chemical kinetics, that is order of reaction. So mainly questions are based on this order of reaction, especially zero order reaction and first order reactions. So here first of all, what is the order of reaction? Order of reaction is nothing but the sum of powers of the sum of powers of concentration terms, the sum of powers of concentration terms in rate equation. The sum of powers of concentration terms in the rate equation or rate law or rate expression, rate law or rate expression, that is called order of reaction. So here for example, I am taking one example here. A plus B is gives rise to product C. So for this let us consider rate is equal to K into A power 1 B power 1. So here what is the order here? So here order is sum of powers of concentration terms. So here what are the concentration terms? 1 plus powers of power values of this concentration terms 1 plus 1 means 1 with respect to A, 1 with respect to B. So total order here it is second order, second order reaction. And when you consider A is gives rise to product C, so when you write the rate, hypothetical only I am taking here, rate is equal to K into A power 1. A power 1 means here order is equal to what is the power value 1. So it is the which order reaction? First order reaction, first order reaction. And if you take the A plus B, 2A plus 1 by 2 B is gives rise to product C. If it is give rate equation, rate is equal to K into A square B to the power 3 by 2, like that it is giving. Okay, so what about the order here? Order is equal to K into, sorry, order is equal to here 2 with respect to A, 3 by 2 with respect to B. So here total order here 7 by 7 by 2, 7 by 2, total order is 7 by 2. And for some reactions A plus C plus D is gives rise to product P. So here let us consider rate is equal to K into, all this data we are getting from the experimental values only. All this information we are getting from experimental data only. So here rate K is equal to A power 1, C power 2, D power minus 1. So here order with respect to A is 1, order with respect to C is 2, order with respect to is negative minus 1. So total order is equal to 1 plus 2 plus minus 1. So total order is second order. Means here children, what we can understand here, the order of the reaction may be positive values possible, and maybe fractional values are also possible, and even negative values also possible. So order of reaction, n value may be positive, negative, or fractional. Fractional values are also possible, negative or fractional values, fractional values are also possible. Okay, that is about the order of reaction. Okay, means you can consider it as a characteristics of order of reaction. So here order of reaction can be identified by experimental data. Order order of reaction, order of reaction can identify by using experimental data only. Experimental data means by simply seeing the reaction we cannot predict the what is that particular order of reaction. So here we can take examples like, say for example, CH3. Okay, let us go through the simple examples. First, let us take one real example here. So 2HI is gives rise to H2 plus I2. So it is one of the example of second order reaction. Rate is equal to K into Hi to the power 2. So it is a example of a second order reaction. Next to go to the first order reaction here. Let us take a formation of or zero order reaction. H2 plus Cl2 in the presence of H nu. It is gives rise to HCl. Here rate is equal to K into H2 to the power 0 Cl2 to the power 0. Means rate not at all depend on the concentration of hydrogen and chlorine. So here it is example of what? Zero order reaction. Zero order reaction. So this order is also depends on what? Conditions. Conditions also affect the order of reaction. Next you take the 2O3 2O3 is gives rise to 3O2. So here when you write the rate, so here rate is equal to K into O3 square O2 to the power minus 1. Means order with respect to ozone is 2, order with respect to ozone is 2, and order with respect to oxygen is minus 1. So all this information we can get from the experimental values only. So from this we can conclude that order of reaction we can write or we can get from the experimental data, but simply by seeing the balanced chemical equation we cannot write the order of reaction. Okay, so but for elementary reactions means simple reactions which are complete in a single step. For them we can write order of reaction by using the this stoichiometric coefficients, but complex reactions it is not possible. Okay, so this is about what? Order of reaction. So what is order of reaction means? So the sum of powers of concentration terms in rate equation or rate law or rate expression are called is called what? Order of reaction. So these are the some examples. So here order may be positive or may be negative or it may be fractional. Whatever it may be, can identify by using experimental data only. By simply seeing this balanced equation, we cannot say order of reaction or we cannot predict the order of reaction. Okay. Next, let us discuss about the different type of order of reactions. Next, let us discuss about different type of order of reactions. First, zero order reactions. Zero order reaction. So what is a zero order reaction? So zero order means the sum of the powers of concentration terms is equal to zero. Such type of reactions are called what? Zero order reactions. So what is a zero order reaction here? If n equal to 0. If n equal to 0 means children the sum of powers of concentration terms. The sum of powers of concentration terms in rate equation is equal to equal to 0 is equal to 0. Such type of reactions are called what? Zero order reactions. Okay, say for example, let us take, okay, H2 plus Cl2 in the presence of sunlight, this gives rise to 2HCl. It is one of the example of zero order reaction. And H2 plus I2 or decomposition of HI, decomposition of HI to HI on the gold surface, on the metal surface, to form as H2 plus I2. It is also example of zero order reaction. And decomposition of ammonia, decomposition of ammonia to NH3 molybdenum, take the molybdenum, iron and molybdenum, iron molybdenum, it gives N2 plus 3H2. So all these comes under what? Zero order reaction. So zero order reaction means rate is equal to k into a power 0, means they are not at all depending on the rate of on the concentration of reactant, means rate is independent on the concentration of reactant. Such type of reactions are called what? Zero order reactions. So here rate generally will write dx by dt, change in concentration by change in time, that is k into a power 0. So here anything power 0, that is 1. Therefore dx by dt is equal to k. When you plot a graph, when you plot a graph between the rate dx by dt and concentration, so the rate is independent. So rate is independent, and we are going to get a parallel line along with the x-axis. Okay, a parallel line along with the x-axis. So such type of graph here we will get when you draw the graph dx by dt, and this is concentration. Okay, dx by dt by concentration, or sometime it is also indicated as to a minus x. A minus x is nothing but change in concentration. So rate independent on the concentration. Such type of reactions are called zero order reactions. Now let us see the zero order kinetics, rate constant for the zero order reaction, or differential rate, differential rate, differential rate for zero order, differential rate for the zero order. Okay, so differential rate for the zero order. Okay, so let us consider a hypothetical equation. Again a is gives rise to product. For this one, how we write the rate expression or rate equation or rate law? So we already know rate expression or rate law, it is nothing but which gives relation between the rate of reaction and concentration of the reactants. That is called what? Rate expression or rate equation. And here rate expression or rate law for this one, rate is equal to k into a power 0. Okay, so here rate is equal to minus dA by dt. So now let us consider initial concentration is A after the time t. Okay, so for the sake of convenience I'm writing here. So let us consider A to P, initial concentration A at t equal to 0, at t is equal to t, consider some of the concentration is decreasing and x amount of concentration is decreasing and the final concentration is A minus x. We can consider it as the A naught initial concentration, A is the final concentration. Okay, so minus dA by dt is equal to k into a power 0. A power 0 means it is not at all going to depend on the concentration or initial concentration of reactant. Rate of reaction does not depend on initial concentration. So minus dA by dt is equal to k. Why? Because here anything power 0 it will become 1. Okay, so therefore minus d of a is equal to k dt, and when you take the integration here, integration minus concentration, initial concentration a naught, final concentration is a, concentration of a, that is equal to k is constant, initial time equal to 0, final time t is equal to t dt. So differentiation integration will get cancelled and we will get here minus of concentration of A minus of concentration of A minus concentration of A naught, that is equal to KT. Okay, now you send this minus sign into the bracket, it will become as A naught minus A, that is equal to KT. So here A naught is the initial concentration, A is the final concentration, and here rate constant for the zero order reaction A naught minus A by T, or K is equal to A naught means that is small a minus A means A minus x, final concentration by T. Now K is equal to A minus A plus x by T. So A will get cancelled out. K is equal to x by T, or x is equal to KT. Okay, so this is about what? Zero order reaction. Okay, next to half-life of zero order reaction. Half-life of zero order. Half-life of zero order. So half-life, what is half-life means here children? Time required for the completion of half of the initial concentration. That is called what? Half-life of the reaction. For example, here we are taking 100 molecules and here we are measuring how much time it is required to convert 50 molecules. This is called T half. And okay, so your time required for the completion of 50% of the reaction, that is called what? Half-life of the zero order reaction. So now T is equal to T1 by 2, A is equal to A naught by 2. So now substitute that values in this equation. Now K will become, K is equal to A naught minus, what is the A value here children? A naught by 2. A naught by 2 by T. Okay. So now here K is equal to, here T is equal to T1 by 2. Time, what we consider time? Time T is equal to 1 by 2. Now k is equal to, children, so 2 a naught minus a naught, 2 a naught minus 2 a naught minus a naught. Okay, one second. So when you do this, k is equal to 2 into, when you take this 2 a naught minus a naught by 2 by t 1 by 2. Okay, so here 2 a naught minus a naught, that is equal to, k will equal to uh, k is equal to a naught by 2 by t half, or simply you can write, you can rearrange this as k is equal to 2, sorry, a naught by t half, or t half is equal to a naught by 2k. So this is the half life of a zero order reaction. Okay, so now let us discuss about the graphs related to zero order reactions. What are the graphs here related to zero order reactions are, we'll discuss. Before that, let us recap this zero order reaction. So here, what is a zero order reaction? Means if n equal to 0, that is called what? Zero order reaction. Means the sum of powers of concentration terms in the rate equation is equal to 0. Such type of reactions are called zero order reactions. Here H2 plus Cl2 examples. H2 plus Cl2 is gives rise to 2HCl in the presence of sunlight. Example of zero order reaction. Decomposition of hydrogen iodide on the gold surface is also example of what? Zero order reaction. Decomposition of ammonia. So a rate is equal to k into a power 0. Rate is generally we write dx by dt, that equal to k into a power 0 dx by dt. So therefore dx by dt is equal to k, means rate of reaction is independent on the initial concentration. So when you draw a graph between the rate of reaction, dx by dt means rate of reaction, and it is the concentration, you get this type of curve. Okay, and when you observe the differential rate for the zero order rate, or for zero order reaction, so we already know zero order reactions. So let us take example here. A is gives rise to product at a time equal to 0, initial concentration is a, or we can consider it as a naught, or a, this is equal to a naught, and final concentration at time t a minus x, that is equal to a. So now here rate is equal to k into a power 0. Here rate is equal to, for this reaction, how we write rate? Change in concentration. As it is reactant, here we are keeping minus sign, minus dA by dt is equal to k into a power 0. So here anything power 0 means 1. Therefore minus dA is equal to k dt, and integrate this equation. So when you integrate this equation, we are taking limitations a naught to a, initial concentration to final concentration, and here limitations initial time to final time. So when you solve this, you'll get minus of concentration of final concentration minus initial concentration, that is equal to kT. And when you send this minus sign into the bracket, you'll get a naught minus a, that equal to kT. And here k is equal to a naught minus a by t, where k is equal to a naught. A naught is initial concentration a is the a minus x final concentration. When you substitute all these values, and when you do this, you will get k is equal to x by t, means the rate constant is independent on the initial concentration, and here x is equal to kt, means change in concentration is independent on the this rate of reaction is independent on the concentration term. Okay, here rate depend only on the, sorry, rate also does not depend on the time also, zero order reaction. And half life of zero order reaction, what is half life means time required for the completion of 50 percentage of the reaction, that is called half life. So here 100 molecules are converting into 50 molecules, so the how much time it is taking? Half time. So T is equal to T half, then final concentration will be half of the initial concentration. Initial concentration is A naught by 2. So here K is equal to A naught minus A naught by 2. When you do this, you get T half is equal to A naught by 2K. So T half is directly proportional to initial concentration in the zero order reaction. Okay. So now let us see some important information in the zero order reaction. Important information in the zero order reaction. So here equal percentage of reaction completes in same time interval in zero order reaction. Equal percentage, equal percentage of reaction, equal percentage of reaction completes, completes in same time interval, same time intervals. Okay, so the concentration of reactant left after the some same time interval is like arithmetic progression. Okay, we can understand by using the one progression here. See, 100 molecules, 100 molecules are converting into 50 molecules. Again this, again it is one T half, it is converting into 25 molecules. 12.5, so this is also 1 T half. So here from this expression, T half is equal to A naught by 2K, and when you remove this 2K means a constant, when you remove T half is directly proportional to initial concentration, means initial concentration increases, T half is also increases. If initial concentration is decreases, T half is also decreases. Linearly it increases or linearly it decreases, like in arithmetic progression. Okay, so here for example let us consider 100 molecules are converting into 50 molecules. Let us consider it is taking 1 minute time, and here 50 molecules are converting into 25 molecules. Okay, so here 50 molecules are converting into 25 molecules means concentration is decreased, time is also decreases. So here half time it is decreased, it is also become 1 by 2 minutes, 1 by 2 minutes. It is 1 minute, it is 1 by 2 minute. At 125 to 12.5, so here how much time, how much concentration is decreased? 1 by 4, means it will take 1 by 4 minutes. So like this progression we can get in the zero order reaction. Okay, so time progression. Next to, when you draw the graphs, graphs, what are the graphs related to zero order reaction? So your zero order reaction rate constant K is equal to x by t, or that is equal to a naught minus a by t. So when you draw a graph between the x versus t, means change in concentration by change in time, we'll get a, so here we can convert this x is k is equal to x by t graph like x is equal to kt. So here y is equal to mx type of graph we are going to get. So here change in concentration is directly proportional to change in time. So here like this graph here you will get here slope is equal to k, positive slope means we'll get such type of graph. And when you draw the graph between the rate versus time, so there is no relation between the means rate is independent on the time, always it is having the same rate of reaction. This rate of reaction is independent on the time as well as the concentration. And one more graph, that is important graph t half, t half and initial concentration. So t half in initial concentration, t half of zero order reaction directly proportional to initial concentration. So when you draw a graph you will get like this graph. Okay, only one curve here you will get. So like this graph you will get when you draw a graph between the t half and the initial concentration. Okay, so this is some important information about the zero order reaction. Okay, thank you.